6.2a, sum and difference identities. So today we're going to introduce the new identities, sine, cos, and tan. We're going to use these identities to simplify expressions, and then we're going to find exact trig ratios of other angles not on the unit circle. So if we want to add two angles together, such as sine of 60 plus 30, the identity that would be equivalent to this would be sine of 60 cos of 30 plus cos of 60 sine of 30. Or in general, these are on your formula sheets. Sine, this symbol is called alpha, this symbol is called beta. So sine of alpha, any alpha plus b sine of alpha cos of beta plus cos of alpha sine of beta. Okay? So just in this example, we actually want to verify why this is true. So technically, if 60 plus 30 is technically a 90-degree angle, and if we went to our unit circles, sine of 90 is equivalent to a ratio of 1. If I use the ratios for each of these values, all of this should eventually equate to 1 as well. So sine of 60 on our unit circles gives me root 3 over 2. Cos of 30 also gives me root 3 over 2. Plus cos of 60 is half. Sine of 30 is 1/2. So if I multiplied this together, I would get 3 over 4 plus 1 over 4, which equates to 1. So this is why the identity does work. So when you see sine of 60 plus 30, this entire expression inside the brackets relates to the angle on sine. So it's not like a binomial where you can run sine through your set of brackets. So this does not equate to sine of 60 plus sine of 30. So never, ever, ever run this is not a binomial that we're running sine through the brackets. This entire brackets relates to one big angle. In this case would be 90 degrees. Okay, so this is a no-no. Okay, if you want to evaluate sine of 60 plus 30, we have to go to this identity of sine of alpha cos of beta plus cos of alpha sine of beta. Because if you did do this, right, sine of 60, which is root 3 over 2, plus sine of 30, which is 1/2, this is not going to equate to 1, which is sine of 90, right? This plus this does not equate to 1. So that's why we cannot run this through the brackets, is because this actually is not equivalent to this expression, okay? All right, next. Verify that cos of pi over 2 minus pi over 4 is equivalent to cos of pi over 2 times cos of pi over 4 plus sine of pi over 2 sine of pi over 4. So our cosine sum and difference identities is cos of alpha minus beta should be equivalent to cos of alpha times cos of beta plus sine of beta. All right, so if I subtracted these two values, this is technically just cos of pi over 4. If I went to my unit circle and found these ratio values, this would be 0 times root 2 over 2 plus sine of pi over 2 is 1. While cos of pi over 4 is root 2 over 2 on our unit circle, this would equate to 0, so that just disappears. 1 times root 2 over 2 is root 2 over 2. So that we verified that this is actually equivalent to this identity. Okay? All right, so why do we use sum and difference identities? It's to help values of angles that actually are not on, that aren't directly related to the 30, 45, and 60 degree angle. We can start to separate or add angles to get these exact values. So for example, it says write each expression as a single trigonomic function. Well, 100 would represent our alpha angle in our identity, and 10 would represent our beta angle in our identity. So technically this is sine of alpha cos of beta minus cos of alpha sine of beta. So I'm going to go look at my trig identity and look for what this relates to. So sine of alpha cos of beta minus cos of alpha sine of beta is actually equivalent to just a single trig ratio of sine alpha minus beta. So this would just be equivalent to sine 100, which is alpha, minus 10, which is my beta. So technically this is just sine of 90 degrees. And we're done. Sorry. And we're done. Okay. Similarly, our tangent ratios, right? This is 7 pi over 4 would represent, or over 12 would be our alpha, and 5 pi over 12 would be our beta angle. So looking at this ratio would relate to this ratio. So technically this expression would be the same as just saying tan of alpha, which is 7 pi over 12, minus beta, which is 5. This would be equivalent to just tan of 7 pi over 12 minus 5 pi over 12, which technically we don't really know what these angles are on the unit circle, but when I start to subtract them, I'm going to get a 2 pi over 12, which in turn gives me pi over 6, which is an angle on my unit circle that I could look up. So you can start to get using these identities of angles not directly related to the 30, 45, and 60 degree angles. So which brings us to our next example. So if I wanted to find the exact value of cos of 105 degrees, well, 2 days ago I would say you couldn't do it because this is not an angle on our unit circle. But today we can, because what we're going to do is we're going to separate this into two angles that relate to our 30, 45, and 60 degree angles. So how can I come up with 105 degrees in relating those angles on our unit circle? Well, if I take 45 degrees and I add it to 60 degrees, so these are angles I can find on my unit circle, but if I add them together, I'm going to get 105 degrees. So I can now actually find the exact ratio for cos of 105 by using my sum and difference identities for cos of alpha plus beta. So using our identity, cos of alpha plus beta would be cos of alpha, which is 45 degrees, times cos of beta, which is 60 degrees, minus sine of alpha, sine of beta. So now that I've written this in my sum and difference identity, now we're going to go to our unit circles, look these ratio values up to get our exact ratio for cos of 105. So cos of 45 is root 2 over 2. Cos of 60 would be 1/2 minus sine of 45 is root 2 over 2. And sine of 60 is root 2 over 2, or root 3 over 2. So now I'm going to multiply these. So I get root 2 over 4 minus root 6 over 4. So my exact ratio for cos of 105 degrees would be 2 minus root 6 all over 4. That would be my exact trig ratio. All right, similarly, 7 pi over 12. So now I'm forcing you to work in radians. So this is where fraction values get tricky. I want to somehow come up with the 7 pi over 12 using my pi over 3, or sorry, pi over 6, pi over 4, or pi over 3 rotations. So because this has a denominator of 6, I am going to take those angles on my unit circle and write each of them with a denominator of 12. So pi over 6 would be 2 pi over 12. Pi over 4, pi over 12, and pi over 3 is 4 pi over 12. And then maybe even your 90 degree would be 6 pi over 12. So I need to use a combination of any of these angles and come up with 7 pi over 12. So what would that entail? That would entail these two angles. 3 plus 4 gives me 7. So I am going to rewrite this ratio as a sum and difference of tan of 3 pi over 12, which is technically pi over 4, plus 4 pi over 12, which is technically pi over 3. And now I'm going to write out my sum and difference identity for the tangent of alpha plus beta. So using my sum, which is here, is going to be tan of alpha plus tan of beta divided by 1 minus tan of alpha times tan of beta. So I'm going to write this out using my angles. So this would be tan of pi over 4 plus tan of pi over 3 divided by 1 minus tan of pi over 4 times tan of pi over 3. So now I'm going to go to my unit circle. I'm going to look those values. Tangent of pi over 4 is 1 plus tangent of pi over 3. Well, if we've written out our tangent ratios on our unit circle is root 3. 1 minus tangent of pi over 4, again, is 1, times tangent of pi over 3 is root 3. So what we get is this 1 plus root 3 over 1 minus root 3. All right, a little tricky now. We generally do not want radicals in our denominator, so I have to rationalize this denominator. So thinking back to Math 20, how do I rationalize this denominator? I'm going to multiply this by what we call the conjugate of the denominator. So in my numerator, I'm going to have to FOIL this radical expression, and I get 1 plus 2 root 3's plus 3. And I FOIL that out. In my denominator, when I FOIL the bottom out, I simply get 1 minus 3. So simplifying again, this becomes 4 plus 2 root 3 all over negative 2. I could then divide each of these values by a negative 2, which would be negative 2 minus root 3. So what is my exact trig ratio for tangent of 7 pi over 12? Would be minus root 3. Okay, moving on to example number 4. Simplify the following. Sine of pi over 4 plus x minus sine of pi over 4 minus x. So again, remember, we cannot run this sine through the set of brackets. So technically what I have is 2 sets of sum and difference identities here. Okay, so this is alpha and beta for this identity. This is alpha and beta for this identity. So using my identities, sine of alpha plus beta would be sine of pi over 4 times cos, just x, plus cos of pi over 4 times sine of x. So this is my first identity. And then I'm going to subtract, because I'm subtracting this entire identity, I'm going to put it in a set of brackets. And this will be sine of pi over 4 times cos of x minus cos of pi over 4 times sine of x. Okay, so now we're going to start to evaluate and just clean everything up. So I can look this ratio up on my unit circle, which is root 2 over 2. So I have root 2 over 2 times cos of x. Here I have root 2 over 2 times sine of x. I'm going to run this negative through my brackets. Sine of pi over 4 is root 2 over 2 cos of x. Negative times a negative is going to become a positive, and this is going to be root 2 over 2. All right, so clean this up even more. I have root 2 over 2 cos of x minus root 2 over 2 cos of x. So those are just going to cancel each other out. Now I'm going to collect these together. Technically, I have 2 of these, so I have 2 root 2 over 2 sine of x's. Technically, those 2. So my final expression, simplified expression, would be root 2 sine of x. All right, example 5. Simplify tangent of x plus tan of x to a single trigonomic function. And it's all over 1 minus tan squared x. Okay? So when I think about this, okay, so when I think about this, technically x could represent, this could represent my alpha, and this could represent my beta. But technically alpha and beta in this case are identical. So if I rewrote this as tan of x plus tan of x over tan squared x is technically tan of x times tan of x. So thinking about my identities, that ends up to be the same as this identity. Tan of alpha plus tan of beta over 1 minus tan of alpha times tan of beta. But in this case, alpha is x, and so is beta. Beta is also x. So this it can come directly from my sum and difference identity. I could rewrite this to be tan of x simply plus x, which technically is just tangent of 2x. And we're done. There's our single trigonomic ratio. Okay, and then last example. It says cos of alpha is equal to 3/5, and cos, this should be it, cos of beta is equal to 5 over 13, where alpha needs to be drawn or greater than 0 but less than pi over 2, and beta needs to be greater than 3 over 2, 3 pi over 2, and 2 pi. Find the exact value of cos of alpha. All right, so if I wanted to find the exact value of this, let's expand this expression first. This is my sum and difference identity. So I get cos of alpha, cos of beta, minus sine of alpha, sine of beta. All right, so when I think about this expression, do I have any of these ratios right away? So these ratios that it gives me aren't necessarily directly related to my unit circle. They're given to me in a completely different context. So cos of alpha, it tells me, is 3 over 5. So I can replace cos of alpha with 3/5. I can also replace cos of beta with 5 over 13. But then we don't quite know what sine of alpha or sine of beta is. So that's where this information comes into play. So it tells me that alpha in pi over 2. So that tells me that I should draw this angle, that I should be working in quadrant 1. So I'm going to draw a triangle in quadrant 1. Go off my cosine ratio is 3 over 5, while cosine ratio would be adjacent over hypotenuse. So I'm just using symbol SOHCAHTOA here. And then my sine ratio would be opposite over hypotenuse. So I'd have to use Pythagoras to find my y value. So I get a value of 4. So that means sine of alpha would be 4 over 5. So I can replace that with that ratio. Now I need to find sine of beta. Well, now I need to go to the second piece of information. It tells me that beta is greater than 3 pi over 2 and 2 pi. So this tells me I'm going to draw this angle in quadrant 4. My cosine ratio is again 5 over 13, so adjacent over hypotenuse. Again, I'm going to use Pythagoras to find my y value, because I need my y value for my sine ratio. And this works out to 12. But because I'm working in this quadrant, this value actually needs to be a negative 12. So my sine ratio for beta would be a negative 12 over 13. All right, so now we're ready to simplify and get the value for cos of alpha plus beta. Multiply, I get 15 over 65 minus, well, technically plus, because a negative times a negative would be 48 over 65. Add the two together, 15 plus 48. So cos of alpha plus beta would equate to 63 over 65. Okay. And that is our sum and difference identities.